And at some point there was a calculation of this in about 1980. There was some physicists calculating that this could happen, and they were further calculating that inside that bubble, not only are the laws of physics different and everything, so your particles can't hold together, but also the space in that bubble would itself be unstable. So anything that fell into the bubble would also then be crushed in a black hole, basically. And they calculated that, and then they wrote a little paragraph about it. And I'm going to share that paragraph with you because I think it's one of the pieces of the best pieces of physics poetry and I've ever seen in an academic paper. So they've just calculated that if the vacuum decay happened, the stuff inside would collapse and be destroyed. And they say, this is disheartening. The possibility that we are living in a false vacuum has never been a cheering one to contemplate. Vacuum decay is the ultimate ecological catastrophe. In a new vacuum, there are new constants of nature. After vacuum decay, not only is life as we know it impossible, so is chemistry as we know it. However, one could always draw stoic comfort from the possibility that perhaps in the course of time, the new vacuum would sustain, if not life as we know it, at least some structures capable of knowing joy. This possibility has now been eliminated. So before we get too upset about vacuum decay, I did promise that I would explain why we shouldn't worry about it. And there are a number of reasons that we shouldn't worry about vacuum decay. One is, obviously, you can't do anything about it if it's going to happen. So, you know, why concern yourself about that? Another is you wouldn't see it coming. Also, you wouldn't feel it, because if this bubble is happening at about the speed of light, you know, your nerve impulses don't travel that fast. So there would be no way to notice that it even occurred. There would be no tragic aftermath because it would destroy everything else. Nobody's going to miss you. But also, you know, the chance of it happening based on what we know is just astronomically small. So we can't predict when a quantum tunneling event is going to occur, but we can put a time scale on when we expect it to occur. And the time scale that we calculate for vacuum decay happening anywhere in our observable universe is something like 10 to the power of 100 years. So far into the future, and that's the low end of the estimate. So far into the future that it's, you know, it's virtually impossible that it could happen anytime within, you know, the lifetime of our planet. And you know, well, we technically can't say for 100% certainty. We can be really fairly sure anything that has ever happened to anybody in the history of the world is much more likely to happen to you than vacuum decay is. But the other reason we probably shouldn't worry about it is that our assumption that vacuum decay is even possible is based on assuming that we understand the standard model of particle physics, and that that's the only physics that's important to the universe in this way. And when we look at what the universe is actually made of, we see that most of it is dark energy, which we don't understand, which doesn't fit into our current models very well at all. Most of the rest is dark matter, which is a kind of matter that isn't, you know, contained in the standard model of particle physics. It's probably some new particle, maybe associated with some new theory. And then there's this little 5% slice that contains the entire standard model of particle physics and everything we've ever seen or touched or interacted with. So there are these huge mysteries that we need to figure out before we can really say if something like vacuum decay is even on the table, much less, you know, something we should think about anytime soon. So I usually stop there when I'm talking about these possibilities, but I just want to very briefly go into one more possible end of the universe, which is a bouncing cosmology, because I feel like this one sometimes brings people a little bit of hope. So a bouncing cosmology is any cosmology where you have a transition from an end of the universe to a new beginning. And there are many ways that can happen. And in the book, I talk about several of these possibilities where you can go from sort of a big crunch to a new big bang, or maybe a heat death to a new big bang. And I'll just show a couple of diagrams of some of the ones that I talk about in the book. So one of them is called the Expirodic cosmos. And this was first discussed by my PhD supervisor, Paul Steinhardt, and a colleague of his, Neil Turok, and a few of their collaborators. And they were looking at the possibility that our universe might be a three-dimensional object in a larger dimensional space. So in this image, you can imagine that instead of being a two-dimensional sheet, this is a three-dimensional space. And then this space in between these two sheets is a higher dimension of space that we can't perceive, but it's sort of a direction that's perpendicular to all of our directions, which you can't really think about, but we imagine sometimes in physics. And then there could be another universe that's on another one of these three-dimensional sheets. And these universes could cross that distance and interact with each other. And as they come together, they would disturb each other. They would set up the conditions for the beginning of a new cycle of the cosmos. They would collide with each other. And when they collide, that's a new Big Bang. And then as they come apart, each one is expanding. The one that we live on, which in this image is the darker one, that creates galaxies and all the stuff we see in the cosmos. And then the universe expands and expands and then comes together again, and these things collide again, and you can have this happening over and over and over again. Now, this is the sort of original idea behind the Expirodic scenario. The new ideas based on that same sort of evolution don't necessarily involve higher dimensional spaces, but you would have just in our own universe, in our own space, a little bit of contraction and then a new Big Bang and then a new phase of expansion and so on, driven by a sort of more abstract process. But this idea that you can have a sort of crunching cosmology and then a new Big Bang and a new evolution where the conditions for our early universe are set up by contraction from the time before it, that's all part of this idea, this cyclic cosmology idea. And there are some appealing ideas to that, not just philosophically, but also scientifically. And so this is something that astronomers, physicists and astronomers are looking at. And the last one I'll mention is this one called conformal cyclic cosmology, which is proposed by Roger Penrose, where you can have a universe that evolves into a heat death, end of the universe, and then a new Big Bang comes out of that. And then that you have these eons, they're called eons, these phases of the cosmos, where you have a heat death and then a new Big Bang and so on, over and over again. And one of the intriguing things about this, and also you can get this in the Expirodic cosmos, is it's possible that something could survive through the transition. And so you could potentially see signatures of the previous universe in our universe. And there have been some proposals of things that may be signs of a previous universe, and they're controversial, so we don't know for sure yet if any of that is happening. But in the next few years, we're going to have a ton of new tools to figure this all out. We're going to have the Vera Rubin Observatory, which is going to observe billions of galaxies in the sky and map the expansion very well, and the history of the cosmos very well. We're going to have new observations of the cosmomicrowave background and various features of that, which can tell us something about these potential signatures, but also about the shape of the cosmos and the early evolution of the cosmos. There's proposals for a new, larger version of the Large Hadron Collider called the Future Circular Collider that would be much bigger and reach higher energies and do more powerful collisions where we could examine particle physics. And then there's also plans for space-based gravitational wave detectors, which will measure the vibrations of space-time as black holes collide in the distant universe, and that'll tell us things about gravity, about the shape of space, about the evolution of the cosmos, and sort of how fundamental physics works. So it's an extremely exciting time in physics and cosmology right now, and through gathering all these clues and through trying to understand the cosmos around us, we may at some point learn more about the end of the universe, but also just about kind of how we fit into this cosmos, how physics works fundamentally, and how we can conceptualize how we fit into this bigger picture, which I think is kind of the most interesting part of that. So I'll leave it here, and I will take some questions now, I think. Thank you for listening.
Thank you so much, Katie, for that fascinating talk. There's been quite a few questions rolling in throughout the talk, and we may not be able to get to all of them, but we'll do our best. So the first one comes from George, and George asks, can you explain how a statement such as the universe is 13.8 billion years old can be made, especially in relation to the theory of relativity?
Okay, I'm not sure how relativity is what the connection with relativity there is on this question. But the way that we determine the age of the universe is by looking at the expansion history of the cosmos. So we can see how the universe has been expanding since the beginning. We can watch the expansion by looking at very, very distant galaxies and how they appear to be moving through the cosmos. And so we can get some idea of the history of the expansion of the universe, and we can kind of just extrapolate back to a time when everything would have been kind of really close together. And that's how we get the age if we extrapolate back on the expansion, we get to a number for when everything would have been kind of on top of everything else. We can also see the cosmomicrowave background and use that as information about how hot the universe was and when that happened and how far away it is and so on. And that's how we get an age for the universe. So the age that we determine, this 13.8 billion years, is based on assumptions about the expansion of the universe that are based on measurements of the expansion of the universe, that there are some uncertainties in that. So the exact number could shift around as we get better measurements of the expansion rate of the universe and the expansion history of the universe. But that number is, it's also consistent with like the ages of stars and what we know about the history of the universe. So it's a reasonably solid measurement, although it could move around by maybe a billion years, maybe a little bit less than that as measurements get more precise.
The next comes from an anonymous attendee. There's a lot of conjecture here: dark matter, dark energy, phantom dark energy, etc. Is there any way to validate any of these concepts?
Well, I mean, so we are learning a lot about dark matter and dark energy. Whether or not dark energy is phantom dark energy, again, most physicists would say that there are some sort of theoretical reasons to not expect that dark energy is phantom dark energy, but we are measuring the properties of dark energy by measuring the expansion of the universe. So the way we learn about dark energy is the expansion history of the universe and the history of the buildup of structure in the universe. So how galaxy clusters come together, how galaxies come together, and so on. And that tells us about the expansion history and the impact dark energy has had on the expansion of the universe. The evidence for dark energy existing at all, there's a few pieces of evidence for that. One is the accelerated expansion of the universe, which you really need a new component of the cosmos to explain. And also the sort of shape of the universe as we measure it, which has to do with like whether or not space itself is curved on large scales, which would tell you something about the components of the cosmos. And all these signs point to the existence of this extra component of the universe that we call dark energy. So the idea that there is something out there that acts as dark energy is very, very much accepted because it fits the data better than anything else. And then with dark matter, similarly, we are very confident that there's a new component of matter that is something that doesn't interact with light, at least in the way that we understand it to, but does have gravity, has an impact on structures in the universe, galaxies and galaxy clusters, and the cosmos as a whole through its gravity. And there have been a number of attempts to explain away various phenomena in the universe without dark matter, but dark matter still fits the data better than any of those explanations do. And it's not as weird an idea as people think. A lot of people are really sort of appalled by the idea of dark matter because it sounds like coming up with a new particle to explain stuff that looks weird in the cosmos. But we already know of a particle that acts in a very similar way to dark matter. So neutrinos also, don't interact with light. They don't have charge. They interact with the weak nuclear force. They have a little bit of mass. They can pass through matter in the same way that dark matter can. So it's not that strange to imagine there's another particle that's got some similarities to a neutrino, and that fits the data just much better than rewriting the entirety of relativity to just have this one tweak where in certain situations it acts just like a collection of matter. You would really have to tweak things in such a way so that it acts exactly like matter that collects in galaxies and clusters and acts exactly like the way an invisible particle would. And that's a very that seems to me to be a bigger ask than just there's a particle that has certain properties that are similar to a neutrino, except it's more massive.
Thank you. The next question comes from Sanika. Have we ever seen the entire universe? Is it possible to?
So there is a limit to how far we can see in the cosmos. So I mentioned that if we look the farthest we can see in every direction, we see this background light from the Big Bang. If we look far enough away and we see, if the farther we look, the farther back in time we see, that's because, you know, there's a certain distance where we look that far and it took 13.8 billion years for the light to get to us. If we tried to look farther than that, the light would have had to have taken more than 13.8 billion years, more than the age of the universe, more than the time that has been around for light to be traveling. So that defines our cosmic horizon. That defines how far it is possible to see, because light coming from a more distant place couldn't have reached us by now in all the time there has been. So, and that's a hard limit. We can't see past that. And excuse me. And we likely will never have any way to see past that. So that defines our observable universe, and you know, whatever's outside of our observable universe is going to remain something of a mystery. Now we can try and make inferences about it based on our theories of the sort of overall structure of the cosmos, but it's always going to be inferences, because just the speed of light limitations means that we can't see past that horizon point.
Thank you. Alan asks, if the universe is expanding, why is Andromeda coming towards us? Shouldn't it also be moving away?
Yeah, so the universe is expanding on large scales, but there's still, you know, if things are close enough together, then they've already sort of overcome the expansion of the universe and they'll stay close together. So for example, you know, the expansion of the universe is not moving the Earth away from the sun, because when the solar system formed, there was a whole bunch of matter that formed out of, and the solar system formed out of that matter, and that matter is overcoming the local expansion there. Basically, there's not enough empty space to keep getting bigger in that small region. If there's a place where there's way more matter than there is dark energy, then the matter wins, and the dark energy just isn't important. And it's the same with like Andromeda and us, and like things within our local group of galaxies. There's enough matter concentrated here that it overwhelms the amount of dark energy there is. So like the Andromeda galaxy and our galaxy were both formed from the same sort of big pile of stuff in the early universe. And so we were already close together, and now we're getting closer together from the mutual gravity. So there are clusters of galaxies out there where the galaxies are orbiting each other. They're not moving away from each other. There are groups of galaxies. So there are things that formed nearby enough are colliding and will continue to collide. But things that formed far enough away that there was enough space in between that the dark energy wins in that region, those will never collide with each other. So it depends on kind of how close together things initially were and whether there was enough matter to overcome the dark energy in that region.
Sarah asks, what is the universe expanding into? Should we assume that the universe is only something inside of something?
So we don't tend to assume that there's anything outside the universe that we're expanding into. The universe might be infinite and getting more infinite, which is weird, but that's something that is mathematically sensible for the way that we talk about the cosmos. There is not necessarily any space outside the cosmos. All we know is that the universe is, like, things within the universe are getting farther apart within the universe. So when we talk about the universe expanding, we're really talking about spaces inside the cosmos getting bigger. And that doesn't necessarily imply that there's anything outside the cosmos that we would be sort of impinging upon. And I know that's a very strange concept, but you can have a space that is all of the space, and that space is still getting bigger. Like, that is a thing that can happen in cosmology.
Thank you. It looks like we've just run out of time, so I apologize if I wasn't able to get to your questions. But Katie, thank you so much for such a fascinating talk and for answering the questions you were able to. I want to thank everyone who's been watching at home for joining another How to Academy event and for taking the time. And Katie, thank you for joining us as well.
Thank you for having me. This was a lot of fun, and thanks everyone for your questions and for attending.